So the example is the harmonic oscillator. Harmonic oscillator. And it will illustrate the ideas very nicely, I think. The Schrödinger Hamiltonian is p squared over 2m plus 1/2 m omega squared x hat squared. Okay, I could put x Schrödinger and p Schrödinger, but that would be just far too much. X and p are the operators you've always known. They are Schrödinger operators. So we leave them like that. Now I have to write the Heisenberg Hamiltonian. Well, what is the Heisenberg Hamiltonian? Yes?
It's identical.
Sorry?
It's identical.
Identical? Yes, but I will leave that for a little later. I will just assume, well, I'm supposed to do u dagger u. And as you said, this is a time-independent Hamiltonian. It better be the same, but it will be clearer if we now write what it should be in general. Have a u dagger and a u from the right. They come here, and they turn this into p Heisenberg over 2m plus 1/2 m omega squared x Heisenberg. Okay. That's your Heisenberg Hamiltonian. And we will check, in fact, that it's time independent. So how about the operators x Heisenberg and p Heisenberg? What are they? Well, I don't know how to get them unless I do this sort of u thing that doesn't look too bad, but certainly would be messy. You would have to do an exponential of e to the minus iht over t with the x operator and another exponential. Sounds a little complicated. So let's do it the way the equations of the Heisenberg operators tell you. Well, x and p are time-independent Schrödinger operators, so that equation that I boxed holds. So IH dx Heisenberg dt is nothing else than x Heisenberg commuted with h Heisenberg. Okay, can we do that commutator? Yes, because x Heisenberg, as you remember, just commutes with p Heisenberg. So instead of the Hamiltonian, you can put this. This is x Heisenberg p Heisenberg squared over 2m. Okay, well, x Heisenberg and p Heisenberg is like you had x and p. So what is this commutator? You probably know it by now. You act with this on these two p's, so it acts on one, acts on the other, gives the same on each. So you get a p Heisenberg times the commutator of x and p, which is IH bar, times a factor of 2. So you can put hats, would look better maybe. And then what do we get? The IH there and the IH cancels, and we get some nice equation that says dx Heisenberg dt is 1 over m p Heisenberg. Well, it actually looks like an equation in classical mechanics. Dx dt is p over m. So that's the good thing about the Heisenberg equations of motion. They look like ordinary equations for dynamical variables. Well, we've got this one. Let's get p. Well, we didn't get the operator still, but we got an equation. So how about p dp dt? So IH dp Heisenberg dt would be p Heisenberg with h Heisenberg. And this time only the potential term in here matters. So it's p Heisenberg with 1/2 m omega squared x Heisenberg squared. So what do we get? We get 1/2 m omega squared. Then we get, again, a factor of 2. Then we get 1 left over xh. And then a p with xh, which is a minus IH bar. So the IH bars cancel, and we get dph dt is equal to, the IH bar cancel, m omega squared xh minus m squared x. All right, so these are our Heisenberg equations of motion. So how do we solve for them now? Well, you sort of have to try the kind of things that you would do classically. Take a second derivative of this equation. The second xh dt squared would be equal 1 over m dph dt. And dph dt would be 1 over m times minus m omega squared xh. So d second xh dt squared is equal to minus omega squared xh. Exactly the equation of motion of a harmonic oscillator. It's really absolutely nice that you recover those equations that you had before, except that now you're talking operators, and it's going to simplify your life quite dramatically when you try to use these operators. Because in a sense, solving for the time-dependent Heisenberg operators is the same as finding the time evolution of all states. This time the operators change, and you will know what they change like. So you have this, and then you write xh is equal to a cosine omega t plus b sine omega t, where a and b are some time-independent operators. So xh of t. Well, that's the solution. How about what is p? ph of t would be m dx dt. So you get minus m omega sine omega t a plus m omega cosine omega t b. Okay, so that's it. That is the most general solution. But it still doesn't look like what you would want, does it? No, because you haven't used the time equals 0 conditions. At time equals 0, the Heisenberg operators are identical to the Schrödinger operators. So at t equals 0, xh of t becomes a, but that must be x hat, the Schrödinger operator. And at t equals 0, ph of t becomes equal to, this is 0, m omega b. And that must be equal to the p hat operator. So actually, we have already now a and b, so b from here is p hat over m omega, and therefore xh of t is equal to a, which is x hat cosine omega t, plus b, which is p hat over m omega sine omega t. and pH of t is here. A is pH of t is m omega b, which is m omega is p, so it's p hat cosine omega t minus m omega x hat sine omega t. So let's see, I hope I didn't make mistakes. P hat minus m omega x hat sine omega t. Yep, this is correct. This is your whole solution for the Heisenberg operator. So any expectation value of any power of x and p that you will want to find its time dependence, just put those Heisenberg operators and you will calculate things with the states at time equals 0. It will become very easy. So the last thing I want to do is complete the promise that we had about what is the Heisenberg Hamiltonian. Well, we had the Heisenberg Hamiltonian there, and now we know the Heisenberg operators in terms of the Schrödinger one. So HH of t is equal to pH 1 over 2m pH squared. So I have p hat cosine omega t minus m omega x hat sine omega t squared plus 1/2 m omega squared xh squared, so x hat cosine omega t plus p hat over m omega sine omega t squared. So that's what the Heisenberg Hamiltonian is. So let's simplify this. Well, let's square these things. You'll have 1 over 2m cosine squared omega t p hat squared. Let's do the square of this one. You would have plus 1 over 2m m squared omega squared sine squared omega t x squared. And then we have the cross product, which would be plus, or actually minus, 1 over 2m, the product of these two things, m omega sine omega t cosine omega t, and you have px plus xp. Okay, I squared the first terms. Now the second one, well, let's square the p squared here. What do we have? 1/2 m omega squared over m squared omega squared sine squared of omega t p squared. The x plus 1/2 m omega squared cosine squared omega t x squared. And the cross term plus 1/2 m omega squared over m omega times cosine omega t sine omega t xp plus px. Whew, a little bit of work, but what do we get? 1 over 2m, and here we must have 1 over 2m, correct, 1 over 2m, sine squared omega t p squared, so this is equal 1 over 2m p squared. These ones, here you have 1/2 m omega squared, so it's 1/2 m omega squared. Cosine and sine squared is x hat squared. And then here we have omega over 2, and here omega over 2. Same factors, opposite signs. Very good. Schrodinger Hamiltonian. So you confirm that this theoretical expectation is absolutely correct. And what's the meaning? You have the Heisenberg Hamiltonian written in terms of the Heisenberg variables, but by the time you substitute these Heisenberg variables in, it just becomes identical to the Schrodinger Hamiltonian.